Alright, the last section that we're going to discuss in Chapter 8 is Section 8.8, the IGBT, which stands for Insulated Gate Bipolar Transistor. Fairly new device. It combines features from both the MOSFET and the BJT, and that makes it useful in high voltage and high current switching applications. Underline that application. Very important for this device. Alright, of course you have to know the symbol for the IGBT as shown in figure 851. The IGBT is a device that has the output conduction characteristics of a BJT, but is voltage controlled like a MOSFET. You can see it's a combination of a BJT and a MOSFET, the IGBT. It is an excellent choice for many high voltage switching applications. Remember, there they name it again. It's an important characteristic of this device. The IGBT, of course, has three terminals called the gate, collector, and emitter. So you can see the combination. And referring to the symbol, you can see that it's similar to the BJT symbol, except that there's an extra bar representing the gate structure of a MOSFET rather than a base in figure 851. Right, the IGBT has MOSFET input characteristics and BJT output characteristics. BJTs are capable of higher currents than field effect transistors, but MOSFETs have no gate current because of the insulated gate structure. So IGBTs exhibit a lower saturation voltage than MOSFETs and have about the same saturation voltage as BJTs. IGBTs are superior to MOSFETs in some applications where they can handle high collector to emitter voltages exceeding 200 volts and exhibit less saturation voltage when they are in the on state. IGBTs are superior to BJTs in some applications where they can switch faster. In terms of switching speed, MOSFETs switch fastest, then IGBTs, followed by BJTs, which are the slowest. But you can have a look at the comparisons between these three devices in table 8.1. Sorry. Alright, let's have a look at the operation of this device. The IGBT is controlled by a gate voltage just like the MOSFET. Remember, this is a combination of the two devices. Essentially, an IGBT can be thought of as a voltage controlled BJT. Of course, a BJT is current controlled, but with faster switching speeds. Because it is controlled by voltage on the insulated gate, the IGBT has essentially no input current and does not load the driving source. Important. A simplified equivalent circuit for an IGBT is shown in figure 852. The input element is a MOSFET and the output element is a bipolar transistor. When the gate voltage with respect to the emitter is less than the threshold voltage, the device is turned off. The device is turned on by increasing the gate voltage to a value exceeding the threshold voltage. The NP-NP structure of the IGBT forms a parasitic transistor and an inherent parasitic resistance within the device as shown in red in figure 853. These parasitic components have no effect during normal operation. Underline that because this is important in the operation of the IGBT. However, if the maximum collector current is exceeded under certain conditions, something happens. The parasitic transistor QP, as we can see in figure 853, can turn on. If QP turns on, it effectively combines with Q1 to form a parasitic element as shown in figure 853, in which latch-up condition can occur. Now this is the problem. In latch up, the device will stay on and cannot be controlled by the gate voltage. And latch up can be avoided by always operating within the specified limits of this device. So you have to know this, figure 853, and explain to me what happens here in this parasitic components of the IGBT that causes latch up. And what is the conditions for latch up? Ne? Anyway, it's discussed there in the last paragraph on page 408, and the figure is on page 409, figure 853. Alright, that's just the introduction to the IGBT, section 8.8, and that concludes this section and also the work that we're going to do for chapter 8.